All right, we've just learned about the definition of continuity at a point for a function. And I've got a couple more things I want to look at. First is one-sided continuity, which is a concept that we can have. So let's take a look. A function f is continuous from the right at a number a if the right-handed limit as x approaches a of f of x equals f of a. And it is continuous from the left at a number a if the left-handed limit of f of x as x approaches a is equal to f of a. I think these definitions are pretty straightforward, but let's look at a quick graph. All right, so here is the graph of a function y equals f of x, and we've got a few different x values to consider. Let's start with a and think about this function. If it is continuous from the left, continuous from the right, or neither. And in this case, it is continuous from the left, because if you look at the function value, it's the same as the left-handed limit. And I think just intuitively, this makes sense. It's continuous from the left because at that function value, we can continue staying connected to the function, to the graph, as we go to the left. So this is continuous from the left. And then if we look at b, is this continuous from the left, continuous from the right, or neither? Well, we can see that from the function value, this connects to the right-hand side of the graph, which is a constant function, at least for a while. At least I tried to draw a constant function. It might not be perfect. And we can see here that the limit from the right is just that function value. So this one is continuous from the right. And then if we look at what's happening at c, it is neither continuous from the left nor continuous from the right because the limit doesn't exist here. That is just fully discontinuous. So we can say this is discontinuous just in general. It's neither continuous from the right nor continuous from the left. It is just discontinuous. So that is the concept of one-sided continuity. We've got one more thing to look at. And this is a function being continuous on an interval. So a function f is continuous on an interval if it is continuous at every number on that interval. And then a quick note, if f is only defined on one side of an endpoint of an interval, we understand continuous at the endpoint to mean continuous from the right or continuous from the left. Again, let's take a look at a graph. So here we have a graph of a function, and I've actually labeled different numbers on the x-axis, just so instead of talking about a, b, and c, we can talk about actual numbers. So here we have a graph, and the first part is part of a parabola, and then it stops there, and then there's kind of a break in it, and then we've got part of a linear function, and then it stops. So these are the only two parts where the function is defined. Those are the only two parts of the domain. And if we look at this parabolic part, it is continuous everywhere on that domain. It's not defined at 3, but it is continuous to the left of 3. And so we can say that this is continuous on the interval from -infinity to 3, not including 3. And we don't include 3 because it's not defined there. That's not part of the domain. This is an open interval, not a closed interval. So that is one part where it's continuous. And then if we look here, we can also say it's continuous on the closed interval from 4 to 6. There are no discontinuities anywhere there. And at those endpoints of the interval, at 4, it is continuous to the right which is good enough for us. And then at 6, it's continuous to the left. And so it is continuous on that entire interval. We are going to continue in the next lesson looking at continuity, because when we know which types of functions are continuous where, that helps us evaluate limits a lot more easily. Because if we have a function that's continuous at a point and we want to know the limit of the function at that point, we know that the limit of the function is just equal to the function value there. So knowing which types of functions are continuous where will allow us to use the direct substitution property in a lot more situations than we have been able to so far.